Hi all, I'm making this video for the test that we took last week. Since we struggle with it so much, I thought I'd make this and try to help you understand it a little bit better, at least show you how it can be done. Um, the first questions here are asking us to write the first four non-zero terms and the nth term of the Maclaurin series. So what we need to know is that the Maclaurin series is a special case of the Taylor series where it's centered at 0. Okay, so quick reminder, the Taylor series is basically a polynomial that approximates our function. The way we find the Taylor series is if it's centered at x equals c, then basically I can write this as f of c plus f prime of c times x minus c plus f double prime of c times x minus c quantity squared over 2 factorial, and I could keep doing this until I get to the nth term, which would be the nth derivative over n factorial times x minus c to the nth power, right? So if you have no idea how to start on these, at least you need to know how the Taylor series is created. And then the Maclaurin series is similar, but our c value is 0, so this is going to be f of 0 plus f prime of 0 times x, because if you plug in 0 for c, just get x minus 0, which is just x, plus f double prime of 0 over 2 factorial times x squared, and the nth term here is still the nth derivative evaluated at 0 over n factorial times x to the n, right? And so this is what it wants for sine. You could go through and plug in 0 to sine, and then plug in 1 and then take the derivative, plug in 0, and you could go through that whole process, but sine is one of the ones we want to remember. It kind of helps to remember that the first term is created by just plugging in c, which in this case is 0. Sine of 0 is 0, so that first term is not really there, and we're really starting with kind of the second term, which is just x, because when you take the derivative, you get cosine. And then the third term goes away because it's sine again when you take the derivative. And we're left with x to the third over 3 factorial. And then we'd get x to the fifth over 5 factorial. It's basically all the odd numbers. Right, so that's the first 4 non-zero terms. The nth Maclaurin for this is going to be just how do I what's the formula for getting this series? And the first thing we need to deal with is the negative. So we can do -1. Let's write out the whole series notation. So we're going to go from n equals 0 to infinity. We deal with the negative by doing -1 to the n power, right? So when I plug in 0, I get positive, plug in 1, I get negative, so on and so forth. Then we have to deal with the exponent on the x. I need to get basically 1, 3, 5, 7. Those are odd numbers, so you can create odd numbers by doing 2n plus 1. Just check that it works, right? If I plug in 0, I get x to the 1. If I plug in 1, I get 2 times 2 plus 1, which is 3, and so forth. And the denominator matches, that factorial matches the exponent, right? So once you know that the exponent's that, you can just write the denominator as the same thing. Right, so that's what number part A should look like. And again, this, and this, you need to memorize, because it's something that's gonna come up a lot, and you don't want to have to recreate it. You don't have time to recreate it. It's expected that you memorize it. So if you haven't done it yet, write it down somewhere, put it on a flashcard, memorize it. Cosine x squared. What we're going to do here is we're going to use a property of something that we learned. So we're going to start by writing. Let's go ahead and write cosine x, which can be approximated by, and that should be an approximate as well, because we didn't find the exact thing. And this should be infinity. I don't know why that was a 0. Cosine x is basically the terms that are missing from sine. So we're going to start with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, right? All the even ones, minus x to the 6 over 6 factorial. That's the first 4. The nth term for this, again, we're not really answering the question right here, but the nth term from this would be, again, we need alternating series. This time we need all the even numbers, which even numbers can just be obtained by doing 2 times n. If I plug in 0, I get x to the 0 power, which is 1. Plug in 1, I get x squared. Plug in 2, I get x to the 4th. And it all needs to be divided by 2n factorial, right? So that's for cosine x. If I wanted to do cosine x squared, well, I basically just replace all my x's with x squared, right? So I'm just going to go through here and I'm going to first just put some parentheses because I'm going to replace the x with something. And I'm going to write x squared, x squared, x squared, right? That is a legitimate answer. We probably should clean it up a little bit, right? Which if we do this, then if we clean it up, we're going to get 1 minus x to the 4th over 2 factorial plus x to the 6th over 4 factorial. Sorry, that's 8x to the 8th. 2 times 4. X to the 8 over 4 factorial minus x to the 12 over 6 factorial. And the nth term is, I mean, you don't have to recreate the wheel, right? It's already created for you. You basically just replace this with x squared, right? So the nth term is going to be almost identical to that, except it's going to be x squared to the 2n over 2n factorial, which cleans up to be using properties of exponents. This is going to be x to the 2 times 2, which is 4n over 2n factorial. So that's the nth term on this one. All right. Part C. If we were going to miss one, I would expect it to be this. It's, you know, this should look like, I don't know if you remember when we had a geometric series, just a normal series. If we started at 0, then geometric was a times r to the n. It converged when r was less than 1, the absolute value of r was less than 1. And if we wanted to find the sum would basically be a divided by 1 minus r. And so when we're looking at this, we're saying, hey, this looks like a geometric series, but we need to rewrite it so it says, you know, so it's in this form, a over 1 minus r. And so the trick is we need this to be 1. So what we're going to do is we're going to basically factor out a 2, right? So that turns it into 1 plus x over 2, right? That 2 can go on the top as 1/2, so it becomes a. And then we need it to say minus, 1 minus something. So the way you make that happen is you do a double negative, right? x 1 minus negative x over 2. And then you have what you need. This is your a, and this is your r. And so you can write a geometric power series for it, which is just a, which is 1/2 times r, which is negative x over 2 to the n. So like we're starting with the nth term here, and it wants the first 4 terms, right? So let's go ahead and write the first 4 terms. Plug in 0. You're going to get basically 0, x to the 0 power, which is 1, so you're going to get 1/2. Plus, plug in 1, you have negative x over 2 to the 1 power, so that's going to be 1/2 times negative x over 2. Plug in 2, you're going to have 1/2 times negative x over 2 squared. 1, 2, 3, it's the first 3 terms. And plug in 3, you're going to have we're just plugging in the numbers for n, right? Plus 1/2 negative x over 2 to the third power. And we could keep going, but it only wants the first 4 non-zero terms. We could clean it up, but you don't really have to at this point. Okay, so now to the next piece here, which is, this part is a bit more complicated. Okay, so because it's centered at 1, we cannot just simply use that formula that we memorized, which again, let me just write this out real quick. We should have memorized the formula for the Maclaurin series for e to the x, which is simply 1 plus x squared over 2 factorial plus x to the third over 3 factorial. It's basically all the x's with the factorials, and the nth term for e to the x is basically x to the n over n factorial. It's a pretty simple basic one, and that's another one you should memorize, but that doesn't apply here because we're centered at 1, and you can't just go through and subtract 1, because the plugging in the 1 to the derivative actually changes the value of the derivative, right? So this is the Maclaurin series. We're asked for the Taylor series, 4th degree, right? So we're looking for the 4th degree Taylor polynomial. So we're going to end up writing that. What we need is the derivatives and the function value, right? So we're going to end up needing f of x, which is this. We're going to need the derivative of f of x, right? Which is the derivative of f of x is 2x e to the x squared. The second derivative is going to require chain rule, derivative of this times this plus, this is going to end up being 4x squared e to the x squared, right? When you take it's basically 2x times the derivative of e to the x squared, which when you take the derivative of e to the x squared, you get 2x e to the x squared. So 2x times 2x is 4x squared. So you get this. And we can keep going. I don't know if we want to clean this up a little bit. I don't know. It might be easier to modify it a little bit, but let's just keep going and see if we need to. The third derivative is going to be, this is going to be that's a constant, so you don't need to use product rule, right? So it's just derivative of e to the x squared, again, is 2x e to the x squared. So this is going to be 4x e to the x squared. Plus, now we're taking the derivative of this over here, which is going to require product rule. So we do the derivative of the first piece, which is 8x times e to the x squared. And then we're going to add that to the derivative of e to the x squared, which is 2x e to the x squared. So it's going to become 8x to the third e to the x squared. And then we're going to find the fourth derivative. One more derivative here. I guess let's clean this up a little bit before we do it. 4x and 8x here, these are actually like terms, right? Because they have the same exponents for the same variables, so we can actually add them. If we added these two, we'd be getting 12x, right? So I don't really want to write that down because I don't have that much space. So let's just remember we have 12x times e to the x squared. When we take the derivative of that, it's going to be the derivative of the first one, which is 12. Derivative of the first one, which is 12 times e to the x squared, plus 2x e to the x, which is the derivative of e to the x squared. So 2x e to the x squared times 12x is going to be 24 x squared e to the x squared. Okay, now we're taking the derivative of this last piece, the 8 cubed. That's going to give us, again, product rule, 24 x squared times e to the x squared plus the derivative of e to the x squared is 2x e to the x squared. When we multiply that by 8, we're going to get 16 x to the fourth e to the x squared. All right, so that's basically our derivative, our derivatives that we're going to need. And now we need to know these things all evaluated at 1. So if I plug in 1 here, we get e, right? When I plug in 1, I get e. If I plug in 1 to the derivative, basically it's going to be 2e. When I plug in 1 to the second derivative, it's going to be 2e plus 4e, which not 4 to the e, 2e plus 4e, which is 6e. When I plug in 2 to the third or 1 to the third derivatives, we get 4e plus 8e plus 8e, which is 20e. And when I plug in 1 to the fourth derivative, we get 12 plus 12e plus 24e plus another 24e plus 16e, which is 48, 50, 60 plus 16, 76e. Right, so these are basically going to be the coefficients. These are the derivatives evaluated at 1. And so our fourth degree Taylor polynomial, we're going to notate it like this. The fourth degree Taylor polynomial is going to look like f of 1, which is e, plus f prime of 1, which is 2e, times x, 2e times x minus 1, right? Because that's the x minus 1, x minus c piece, plus 6e times x minus 1 squared over 2 factorial, plus 20e times x minus 1 to the third over 3 factorial, plus 76e x minus 1 to the third over, to the fourth power now, over 4 factorial. All right, so that's our fourth degree Taylor polynomial centered at 1. And you don't have to do any evaluation, right? It just wants you to write it, and so there we have written it. You don't even need to simplify it. All right. Next one is we want to find a Taylor series representation of natural log of x centered at x equals a. It's not specifying a number of terms, so we just need to come up with the formula for it. So we can just go through it the same basic way by oopsies. Starting with, all right, well, we need f of a, well, we're going to need f of x, f prime, right? F prime of this function of natural log is 1 over x. F double prime is going to be, this is the same as x to the negative 1, right? So it's going to be negative 1 x to the negative 2. The triple prime is going to be 2x to the negative 3. The quadruple prime is going to be negative 6x to the negative 4. And I hope you notice like 6 is 3 times 2, 2 is 2 times 1. Those are like factorials. And then if we plug in a to all these things turn into, so like when we plug in a, this is just going to be natural log a. This one's going to be 1 over a. This one's going to be negative 1 over a squared. This one's going to be 2 over a to the third. This one's going to be negative 6 over a to the fourth. And so we write, all right, let's write our Taylor series. The polynomial is going to look like this. It's going to be the first one, just natural log of a, plus 1 over a times x. The next one's actually going to be negative because it's the coefficient's negative, so it's going to be minus 1 over a squared times x minus a. Ooh, I messed that up over here. This should be x minus a, right? Because it's centered at a. And this should be x minus a squared over 2 factorial. Next one is 2 over a to the third times x minus a to the third over 3 factorial. Let's do the last one just to see if we can find the pattern. The next one's going to be actually minus, because the term is negative, minus 6 over a to the fourth times x minus a to the fourth over 4 factorial. And if we wanted to simplify this before we write our final term, we the first few don't simplify, but then when we get here to this one, I guess this one doesn't really simplify either. But this one will. 3 factorial and then a 2 on the top. 3 factorial is 3 times 2 times 1. So what the 2 does, it cancels out that bottom one, and we just have this. Right? And then the same thing happens with 6. 4 factorial is 4 times 3 times 2 times 1. That 3 times 2 makes 6 and cancels that. And so we're basically left with x minus a to the fourth 4a to the fourth. Right? All that's left of the factorial is the 4. And this will continue. And so we could write the representation for it basically as, notice you're going to have this x minus a piece, right? It's going to be to the n power because it just goes up by 1. It starts at 0, which just cancels out this whole thing, and then goes up 1, 2, 3, 4, 5, so on and so forth. And then the coefficient changes, right? It goes positive, negative, positive, negative. There is like an issue with this guy, right? This natural log is not working for us. So like we can just write that natural log over here, and then instead of starting at 0, we're just going to start at 1, right? Because that first term's not, we're not going to really get that when we plug it into this thing. And so we need a to the n on bottom, right? Because its first one is a to the 1, a squared, a so on, and then an n here because we're getting 1a, 2a, 3a, 4a, and that alternating series thing is going to come from -1 to the n plus 1 in this case, because when I plug in 1, I want to get a positive term, and that gives you the nth term for it as well. Right, I'm going to give you credit for getting to this far, but you know, we should be able to write the nth term for these things as well. Number 3, we're given the Maclaurin series, right? Remember that says we're starting at 0. This is the nth term of the series, and then they're really nice. They actually write it out for you. This is what all the terms look like. Part A says use the ratio test to find r, which is the radius of the convergence, and show the work that leads to your answer. So ratio test is the one where you do the limit as n goes to infinity of the absolute value of a n plus 1 over a n, and you have to show that it's less than 1. You're trying to find the values that make it less than 1. So let's do it. The limit as n goes to infinity. Once I put these absolute values in here, like hopefully by now you're recognizing the absolute value takes away negatives, which basically means, you know, this negative piece is going to be kind of dealt with, but you know, there's a 3 in there, which the 3 does affect it. So let's just keep it for now so we can see what it looks like. It's going to be -3 to the n plus 1 minus 1, which is just n, times x to the n plus 1 over n plus 1. I need a little bit more space here. And we're going to multiply, just divide by the nth term, which in this case is multiplying by the reciprocal. It's going to be n over -3 to the n minus 1 times x to the n. And we're trying to show that this is less than 1. So we do our little tricks and whatnot. And you know, the trick is basically this can just stay as -3 to the n. X to the n plus 1 is the same as x to the n times x over n plus 1 times n over -3 to the n. It can be written as -3 to the n times -3 to the -1, and then x to the n. We're trying to show that it's less than 1. Some things cancel, right? This x to the n is going to cancel that x to the n. This negative 3 to the n is going to cancel that negative 3 to the n. And so what we're left with is much neater. Let's go over here. We're going to go up. We're left with the limit as n goes to infinity of the absolute value of n over n times x over n plus 1. This negative 3 to the negative 1 is going to come to the top and just become like negative 3, right? And we're trying to show that's less than 1. We can factor out the x piece, which in this case is negative 3x, and just do the limit of the n piece, because that's the only thing that the n affects. That's 1, so basically we have the absolute value of negative 3x, which is the same as 3x, is less than 1. We divide both sides by 3, and we get x is less than 1/3, so our r is 1/3, right? This thing here is always our r. Okay, so our r is 1/3. Radius of convergence, 1/3, which means basically if we had number line, it was a Maclaurin series, which means it's centered at 0. We could go out 1/3 to the right, and we could go out 1/3 to the left, and that's where this will converge for x values between negative 1/3 and positive 1/3. What we're not sure about right now is, do the endpoints converge as well? So we need to check those individually, right? So we need to check, let's start with when x equals negative 1/3, which basically just means we're going to take our original function, we're going to plug in negative 1/3, right? Which gives us the infinite series, negative 3 to the n minus 1 times negative 1/3 to the n over n. And we need to figure out if this converges. The first thing I do is try to clean up that top a little bit to see if we can make sense out of that a little bit better, right? Because that looks a little bit weird right now. Negative 1/3 to the n is, let's write both these out. So this one's negative 3 to the n times negative 3 to the negative 1, and this is all over n. Negative 1/3 to the n, and maybe it's helpful I write this over here, is the same as negative 1 to the n over 3 to the n, right? And what this maybe allows us to do is see that if we could clean this up a little bit, then it might cancel with this one. What we need to do is get rid of that negative symbol in there, which if it helps you can think about negative 3 as just being negative 1 times 3, in which case that thing turns into negative 1 to the n times 3 to the n, and then we still have the negative 3 to the negative 1. That's going to bring that 3 down to the bottom, right? So that's going to bring, this piece is going to go down to the bottom. And then we're still going to have negative 1 to the n and 3 to the n. Let me color code this so you see where everything went, right? That yellow piece, let's do this. This green piece turned into this. This turned into that. N is still n. Everything else is just where it was in that previous one, right? And then what now can happen is this can cancel that. And we're left with negative 1 to the n times negative 1 to the n. What do we do when we have two things, same exponent? It'd be negative 1, sorry, same base, different exponents. You add the exponents, you get negative 1 to the 2n, which will always be positive. So this whole thing cleans up to be negative from 1 to infinity, basically cleans up to be 1 over negative 3 to the n, which it looks like a harmonic series, except that it's negative, right? So there's several ways to deal with it. Like right now, you should, like, using your intuition, you should be able to say that this diverges. We could write this as negative 1/3. You can factor out constants, right? Negative 1/3 times times this, in which case you can show that, you know, this diverges, and then multiplying something that diverges by negative 1/3 means it still diverges, right? So here we're just saying this diverges at 1/3, which means, or at negative 1/3, at negative 1/3 has this open bracket on it, right? So now we need to check the positive 1/3. Let's do that over here. So let's check when x equals 1/3. Again, we're just rewriting that series, replacing x with 1/3. So we get negative 3 to the n minus 1 times 1/3 to the n, and this is over n. Many of the same steps can be done here. It's going to be negative 3 to the n times negative 3 to the negative 1. This is going to be 1 to the n over 3 to the n. And again, we can break up this negative 3 to the n and say, well, negative 3 is negative 1 times 3. So that thing turns into negative 1 to the n times 3 to the n. This thing comes to the bottom. And this 3 to the n is still there. 1 to the n is just 1, so it doesn't matter. This is going to cancel that. And so we're left with the infinite series, basically negative 1 to the n over negative 3n, which again you can factor out like a factor of negative 1/3, or you could do something else with it if you want, but let's just do this for now. It's going to be negative 1 to the n over n. This is a alternating series, so all we need to show is that the limit as n goes to infinity of 1 over n equals 0, which is true, and we need to show that 1 over n plus 1 is less than 1 over n. That's also true, right? So we can show that this thing converges. If that converges, then we just take whatever it converges to and multiply by negative 1/3. So the right, we don't really care what it converges to, but what we're showing is the right endpoint does converge, and so the interval of convergence for this one is that, right? Negative 1, from negative 1/3 to 1/3, not including negative 1/3. Next is use the first three non-zero terms to estimate f of 0.1, right? Which means we're trying to plug in 0.1. We're using the first three non-zero terms, which means we're using the things that they gave us right here. F of 0.1 is just plugging in 0.1 for that, right? F of 0.1 is going to equal 0.1 minus 3/2 times 0.1 squared plus 3 times 0.1 to the third, which is, I mean, if this is an FRQ, you just leave it like it is, right? Like, you don't need to simplify it. What is this actually equal to without a calculator? You have 3/2. 0.1 squared is like 1/10 squared. So that's like 1/100th or 0.01 plus 3.1 cubed is like 1/10 cubed, which is 1/1000th or 0.001. And so keeping on going, we're getting 0.1 minus, that's going to be 3 over 200 plus 3 thousandths. So this is 0.1 minus 3 over 200. We can do that division real quick. 3 thousandths is basically 0.003. Let's do 3 divided by 200 real quick. 3 divided by 200. You can't, no, that's the wrong way around, isn't it? We're trying to do 200 divided by 3 divided by 200, right? So you can't do it at first, so you put a decimal. Even when you do 30, still can't do it, so you got to put another 0. Right, so you got to have 2 zeros. 0.0, then you get to 300, and you're like, oh, 2 that goes in once. You have a remainder of 100, right? 200, you're going to get a remainder of 100. That doesn't go in at all, so you put another 0 there, and you're getting 200 goes in there 5 times. And so you're getting, so this goes in 5 times, which gives you a perfect 1,000, which gives you 0. So this is basically negative 0.015, right? And if we were subtracting these, we'd do sorry, this one should be plus over here, 0.1 minus 0.015 plus 0.003. So this is like just normal subtraction, right? Let's do these two first. Right? How do I do this? Well, I gotta borrow. I can't do 0 minus 5, so I gotta borrow something. So I'm gonna borrow from here. Make this a 9. Sorry, make this a 9. No, make this a 0, which turns this into 10, and you borrow from there, make it a 9, turn this into a 10. So you're gonna get 5, 8, 0. So that's 0.085. And now we're going to add 0.003, which that one's pretty easy, 0.088. And so that's, if we wanted a decimal approximation, that's what we should be getting. Next, it asks, what is the maximum error for the upper bound for the error for 0.01, which since this is an alternating series, right, it goes back and forth. The maximum error just occurs for the next term. We use the first 3 non-zero terms, so that 4th term will give us the maximum error. The 4th term in this one is, we determine it by this, right? So we're going to do the 4th term. Maximum error is the 4th term, which we plug in 4, we get negative 3 to the 5th over 5 times x to the n, which is 0.1 to the 5th. And the thing about the maximum error is you don't really care about negatives. So this is going to be the same thing as 3 to the 5th over 5 times 0.1 to the 5th. There's no reason to actually like go any farther than that. That's the maximum error. Right? It's just the next term in an alternating series is the biggest the error could possibly be. All right. We're going to do these via intuition, remembering that this diverges. So anything bigger than this also diverges. Remembering that this converges, something smaller than that converges as well. Also remembering that this converges if the absolute value of r is less than 1, right? Geometric series, and then some other stuff that we can do. So rewriting this, we could write, since it has a negative exponent, 5 over n. 5 over n is bigger than 1 over n, right? So this one diverges, right? It's bigger than the harmonic series 5, so diverges, right? You don't need to show your work. You're just trying to do it based on intuition and knowing. This is like direct comparison test is good for intuition. It's just hard to show sometimes. 1 over n times 2 to the n, right? Like, why don't we compare it to 1 over n squared real quick? Which one of these is going to be bigger? Well, raising a thing to the 2n power is, bigger, which means you're dividing by a bigger number, which means this one's less than that one, which means this one converges, right? Converges, because this has got to be smaller than that. Raising a number to the nth power, 2 to the n power is smaller than n squared. Next one we have n over e to the n, which me intuitively, I can see that this is probably going to converge just because e to the n is growing much faster than n. It grows much faster than 1 over n does. So, but let's use, why don't we use a limit comparison test with 1 over n squared, right, with that p series. So we're going to do n, we're going to do the limit as n goes to infinity of n over e to the n divided by 1 over n squared, or multiplied by n squared over 1. This is going to give us the limit as n goes to infinity of n to the third over e to the n, which goes to 0, right? Exponentials grow faster than those, which means the limit exists, which means they both converge, right? Next one. Like if we wrote this, it would be n plus 1. If we like multiplied that in, it'd be n squared plus n, which if we're trying to compare it to something, then it kind of looks like 1 over n. Can we show that it's always bigger than 1 over n? Not really, so let's do a limit comparison test again. We know that this diverges, so we're going to try to show that that diverges as well. So we're going to do the limit as n goes to infinity of our given series times the reciprocal of the other one, which this is going to give us n squared plus n over n squared plus n. As n goes to infinity, this goes to 1. The limit exists, therefore they both have the same convergence or divergence. We were comparing it to the harmonic series, which diverges, so they both diverge. This one is a, I don't know if you remember absolute convergence, but basically absolute convergence means if you take the absolute value and that converges, then the original thing converges as well. So like we could just check like to see, does this converge, right? And if this converges, then the original converges as well, because the original will be smaller than this, right? So like, does this converge? Well, let's compare it to something we know converges. 1 over n squared. 1 over n factorial is definitely smaller than 1 over n squared. So this is absolutely convergent, which means the original also converges, right? N over n plus 1 to the n, I mean, honestly, like, that's, like, it's going to converge. Like, look how fast the denominator is growing compared to the numerator. It's going to converge. But if you had to do a test for it, like, since there's an nth power, let's use the nth root, which the nth root just says the limit is n goes to infinity of the nth root of whatever you have, right? Which this simplifies to the nth root of n. The limit is n goes to infinity, the nth root of n over n plus 1, because the nth root cancels that. And this goes to the limit as n goes to infinity of 1 over n plus 1, which goes to 0, which in this case, it's kind of like ratio test. You have to show that it's less than 1. So it converges. If it were me on a test, you know, you can pretty much tell visually that this is going to converge because the denominator is like significantly growing much faster than the numerator. For number 7, this is an alternating series, right? It has this, so we could do alternating series tests, but alternating series test actually fails because if you do the limit of that, then you don't get 0. So we can try some other things. Oh, you know what we can do? We can just do the normal nth term test, right? Let's just do nth term test, which is take the limit as n goes to infinity of -1 to the n minus 1. Like the nth term test, you just take the whole thing, right? We're just going to take the limit as n goes to infinity of this. So basically, this piece here is going to go to 1, right? This is going to go to 1. And this piece here alternates between positive and negative 1, right? So you have positive and negative 1 times 1, which if you graphed this, basically, you know, your numbers are going to be are going to get close to 1, and then this one's going to get close to -1, 1, -1, 1, -1, 1, -1. That is not converging, right? They're not getting closer to each other. They're just staying at 1 and -1. So this one diverges. 1 over n to the 5n plus 1. Again, we could just compare this to 1 over n squared, right? 1 over n squared is much larger than 1 over n to the 5n plus 1. This converges, therefore that converges as well. Right? Like direct comparison tests, like the reasoning behind it is actually, if you don't have to like show all the steps for it, is actually like your best friend, because you can just like, if you can find one that converges and you know one that, you know this thing has to be smaller, right? You can totally see this has to be smaller than this because the denominator is growing faster. Then you can just say, well, it for sure converges then. All right, so hopefully it's helpful. Hopefully you actually watched it. Thanks for watching it. If you did watch it, hopefully we'll do better in the future on these things.